Has it started or not? Yeah. So good morning, everyone. Welcome to the Bangalore Theory Seminar Series. This week, we are excited to have Arnab Maiti as our guest speaker. He is currently a PhD student at the Paul G. Allen School of Computer Science and Engineering, University of Washington, jointly advised by Professor Kevin Jamieson and Professor Lillian Ratcliffe. Prior to joining Washington, he obtained his bachelor's and master's degrees from the Indian Institute of Technology, Kharagpur, and also spent some wonderful time doing theoretical research at IISc. His current research focuses on design and analysis of algorithms in the areas of game theory and learning theory. Today, he would be giving a talk on his recent work on instance-dependent sample complexity bounds for zero-sum matrix games, which got accepted in IIStats 2023. So
Yeah,
it's all yours.
yeah. Thanks for the introduction. Yeah. I'll be talking about this our recent paper on instance-dependent sample complexity bounds for zero-sum matrix games. So before we go to that setting, let's quickly have a look at what exactly is like two-player zero-sum games. So in this setting, you have like two players, X and Y, and usually the X player has some M different strategies or actions that it can take, and similarly the Y player has some N different strategies that it can take. So the so what happens here is that if the player X chooses a strategy I and the player Y chooses a strategy J, then the X player receives a reward of some Aij and the Y player receives a reward of minus Aij. So the reason why this is a zero sum game is because the sum of rewards that X and Y get is always zero. So one of them will be getting Aij and the other player would be getting minus Aij. So this zero sum game can be very concisely represented by a single matrix, a matrix A, which belongs to R n cross M. So it's in the space of n cross M matrices. Uh, so just let me go through some notations and then I'll go to the problem setting. So delta M is called the m-dimensional probability simplex. So so in the space of m different coordinates, this is the probability space that you can define. So in games, usually the most important concept that usually researchers look at is the Nash equilibrium. So we say a particular pair X star Y star is a Nash equilibrium if this inner product X star A Y star is less than X star A Y and is greater than X A Y star. So let me just spend a minute here to explain what this inequality exactly means. So what's exactly happening is that the player X player is choosing some strategy with respect to this distribution. Essentially, these are both distributions. So the X player is choosing a strategy with respect to this distribution, and the Y player is choosing some strategy with respect to this distribution. So X star A Y star is essentially the expected reward that the X player is getting, and it's also the loss what the Y player is getting. So what this part of the inequality says is that if the X player changes its distribution from some X star to X, it cannot gain more reward. Okay, it cannot do better. So with respect to X player, it's in an equilibrium. Similarly, with respect to the Y player, uh, so for Y player, these are the losses essentially. So if it changes its distribution, it cannot decrease its loss. It can only increase its loss. So this X star Y star is essentially an equilibrium, and this is a very important concept in game theory. So just to give you more idea, let's look at this particular example. So say you have a matrix 3, 2, 1, 4. So you can calculate the equilibrium as for the X player, which is whose action space is the rows, and the Y player whose action space is are the columns. So for the X player, the equilibrium here would be 0.75 and 0.25, and for the Y player, it will be 0.5 and 0.5. Now, like my aim here is not to show you how to calculate it, but just to show you, or just to convince you that this in fact is the equilibrium of this matrix. So first you can easily calculate the expected reward like X star A Y star, and that would be equal to 2.5 here. Now, if you take say X star and multiply it with A transpose, essentially you are taking X star and multiplying it here column wise and here column wise. Then what will happen is that whatever strategy Y player chooses, assuming that the X star is fixed, the Y player cannot get better than 2.5. It's always going to get 2.5. Similarly, if we fix Y star, which is half and half, then whatever the X player plays, it cannot do better than 2.5. So at the end, this particular inequality will hold. In this case, it will be equality, but there can be inequalities also. But uh, so here X star Y star is a Nash equilibrium. So this X star A Y star, I denote it as the value of the game, and a shorthand notation would be like VA star. So due to von Neumann's minimax theorem, what you can show is that if you take this inner product XAY and do maximum over all probability distributions X and minimum over all probability distributions Y, that would be equal to minimum over all probability distributions Y and all maximum over all probability distributions X. So essentially, max min equal to min max, you have this property. So essentially, because of this property, you can formulate any zero sum game as a linear program and find the Nash equilibrium in polynomial time. So this is a very key property. So this is like in the case where you know the matrix completely. Now, we'll be our work mainly focused on this noisy setting, and you can think this problem as some extension of multi-arm bandits into the matrix game setting. So in this setting, you have some matrix say, but that matrix is not directly available to you. But the only thing that you can do is like you can query some element ij of the matrix A and then receive a value xij, which is like some the entry aij plus some noise, and that noise is like some zero mean one sub Gaussian noise. So essentially, um, you go and have a look at a matrix and you can sample one particular entry of a matrix and you will see some noisy version of that element, and you can kind of do this for every entry and try to get an estimate of the matrix and maybe try to compute some kind of approximate Nash equilibrium, and that would be our aim in some sense. But before we proceed, does anyone have any question regarding this noisy setting?
So you're only focusing on two-player games, or what kind of games you're
Yeah,
focusing on?
two player zero sum games.
Oh.
Yeah, this is purely two player zero sum games. So, yeah, not anything. Yeah.
Can you repeat the comparison to matrices of zero sum games that I didn't catch fully? Why zero sum?
Which one?
So two player zero sum game. So zero sum. Can you just add some light on that?
Yeah. So zero sum is coming here, right? Like, so what I assumed is that if X player chooses a strategy I and Y player chooses a strategy J, then X player receives a reward Aij and the Y player receives a reward minus Aij. So essentially the sum is zero. So essentially for every pair ij, there is only one value associated with it. So you can just represent it using one single matrix. And both players are kind of trying to maximize the rewards that they get, but the rewards are totally opposite. Like, for example, +1 and -1. So the sum would be 0. That's why it's zero sum matrix.
Yeah, got it.
Yeah.
Thanks.
Okay. So I hope the setting is clear. Like, essentially you don't have the origin, like the matrix with you, but only thing you have is this query model where you can look at an entry of a matrix and take a sample, and you'll observe some noisy value of the entry. So that's the rough idea. So here we are looking at two different solution concepts. So the first solution concept, we call it as like epsilon good solution. It's not a well-known solution concept, but I'll tell you why we are looking into this. So we aim to find a pair x comma y such that this inner product xay that which is nothing but the expected reward that the X player gets, that is pretty close to the value of the game. So essentially this VA star minus this inner product absolute value should be less than equal to epsilon. So this, if such a pair XY, we denote it as epsilon good solution. And second thing is like a very well-known solution concept, which is you want to find a pair XY such that, like, I'll tell you intuitively what's going on here. So essentially both players are kind of trying to maximize its rewards, or in other sense, the X player is trying to maximize its reward and the Y player is trying to minimize its loss. So here, if you manage to find a pair XY such that even if the players deviate from this, they cannot do anything better than some epsilon value. So to be precise, if you have, let's think from the perspective of X player. So if you take XAY and you consider any other X prime, then the inner product X prime AY would be at most like epsilon times better than XAY. And same is the case here. Like if you consider any other Y prime, then the loss that the Y player would get would be at most like epsilon times less than the actual thing. Like the difference would be at most epsilon. So just like intuitively speaking, none of the players can like improve their situation by some more than some epsilon reward. So that's the rough idea of this epsilon Nash equilibrium. So
So one question is, epsilon Nash is well studied, but epsilon good, what is the? Because I mean, it's not an equilibrium. It is not an equilibrium. So what is the advantage of?
Okay, I almost skipped before going that. Okay, I forgot to tell. So what one can show is that any epsilon Nash equilibrium is an epsilon good solution. So if you like provide lower bounds for epsilon good solution, that will also translate to lower bounds for epsilon Nash equilibrium. Like by lower bounds,
Yes.
I was going to explain the problem, but like if there is any hardness in finding epsilon good solution, then there will be like equal or more hardness in finding epsilon Nash equilibrium. So that's the main objective that we looked at. Like that's the reason why we are mainly studying this. We'll be also giving some upper bound results on epsilon good solution. The way to interpret that would be that you're trying to find some x and y such that, okay, they're not in equilibrium, but with respect to the value of the game, they're pretty close. Like you can say it's an equivalent version of like stochastic optimization extended to this min-max setting. So you want to find some xy such that the function value is pretty close to the original VA star. But that's not why we studied this concept. We mainly studied this particular concept so that we can establish good lower bounds for epsilon Nash equilibrium. So
even you're trying to estimate, it's more like an estimation problem that you want to find what is the value of Nash equilibrium, and then epsilon good solutions are helpful?
Like epsilon good. Okay, so okay, okay. Let me present in this way. For this particular, theoretically, epsilon good solution is pretty helpful to establish like lower bounds for epsilon Nash equilibrium.
No, so that I understood. The lower bound part I understood. The upper bound motivation, that is not clear.
Yeah, like so the way I see it is that you're trying to like, okay, in this case you may not be able to like say like guarantee any kind of equilibrium, but what you can guarantee is that both players are getting like rewards which are pretty close to the value of the game, or the X player is getting a reward which is close to the value of the game, and the Y player is getting a loss which is close to the value of the game. So that's the kind of, like, it's not exactly a motivation, but you can say that this is still some decent solution concept to look at. Like the way I was thinking was like, I'm just trying to extend what happens in like stochastic optimization in general. Like they try to find some x such that the function value in expectation is close to the optimal function value. So you can think this problem in the mathematically speaking, you can think this as also an equivalent version. Like this is the optimal value, like optimal min max value, and you are trying to find some x comma y such that the value of the function is pretty close to the optimal min max value. So that's one way to interpret it. But honestly speaking, like we didn't have any strong motivation to look at it. It's just that this served as a good lower bound for this particular thing. So we like showed like we mainly analyzed this to show the lower bounds, and since we were showing lower bounds for this, we also showed upper bounds just to like close the gap and say that the lower bounds are essentially tight.
Okay, thanks.
Yeah.
So one question I had was because this is linear and therefore convex, like you can use iterative solutions. Is that what you're doing? Like iteratively improving x and y and so on?
No, okay. The main issue is, okay, let me just tell the problem that I'll be looking at, and then I'll answer your question. So the aim is like you have the like, okay, the thing is you don't know the matrix, what matrix A is, because if you know the matrix A, then you can directly compute the Nash equilibrium by just linear programming. So you don't know the Nash equilibrium, but what you can do is like you can take samples from the matrix, and the main goal is like to minimize the number of samples required to find those solution concepts. So you have to minimize the number of samples you take from the matrix and determine these solutions. So the main challenge that you face is like, what is the right number of samples that you must take from every entry of the matrix, and before which you can like conclude, okay, what the epsilon Nash equilibrium might be a epsilon good solution. To give you a rough idea, like the way we like at the, suppose I know how many times I have to sample the matrix, then I sample that many times, and towards the end I just like return the Nash equilibrium of the empirical matrix that you have, and we can show that the solution concept there is pretty good enough. Like those are either epsilon good solution or epsilon Nash equilibrium. So that's the key idea that we had.
So let me understand this correct. So let's say you have the epsilon given to you beforehand, and you know the amount of noise, so you can apply Hofding. Sample the A so many times, get A to epsilon accuracy, and then compute this directly through LP. But you are not doing
LP. Yeah.
Okay.
Yeah. So that's
I think the point is he's not sampling all the entries in some way. So all n-square entries you are sampling.
Yeah. So the thing is like, yeah, that's what I was kind of going to like in. Let me take. Okay. So as like I did not see the name, sorry, but like whoever was suggesting, like what you can do is like this is a very simple algorithm where you can like you can sample 1 by epsilon square and entries from each element of the matrix, and then you can just return the Nash equilibrium of the empirical matrix A bar. Okay, and why you can do that is like you can use the Hofding, or in this case you have like sub-Gaussian tail bounds. Like if you sample sufficiently, then the elements would be pretty close to each other. Okay, and then you can do some series of calculations and show that the Nash equilibrium of the empirical matrix is an epsilon Nash equilibrium. So that's the rough thing that you can show. Like, but the thing is that this is a worst case worst case algorithm. Like in worst case, you are going till 1 by epsilon square. The question that we wanted to address was, can you do something better than 1 by epsilon square? Or like, let me, yeah. So, okay. So for example, like in multi-arm bandits, say if you have some series of arms and you want to, or in if someone doesn't know multi-arm bandits, like say if you have some coins and you want to find the highest biased coin, okay, up to some epsilon accuracy, or in multi-arm bandits they call it as epsilon best arm. In worst case, you can like sample every arm for 1 by epsilon square times and uh, get the epsilon best arm. But there are like instance dependent sample complexity bounds in to identify best arm, where the number of samples depend on the gap between the best arm and the remaining arms. So that's very well studied in multi-arm bandits. We aim to do something similar here in zero-sum games. It's like essentially in a zero-sum game, you're given a matrix, and the matrix is essentially an instance. So depending on the instance, sometimes it might be easy to find an epsilon Nash equilibrium, or sometimes it might be pretty hard to find an epsilon Nash equilibrium. So we want to capture this property of the matrix and give similar sample complexity bounds that arised in multi-arm bandits case. And it's
I see.
pretty, yeah. So that's what we are trying.
So let's say the value of Aij is high. In
Yeah.
that case, it will influence the x and y much more, so you want to sample it more. Whereas if Aij is close to 0, you want to sample it less, or some equivalent of that. Got it.
Yeah, that okay. Ideally that is also one thing we can do, but I'll be focusing on something slightly different that I'll come to. Like I'll just come to it now. And an easy thing to observe that the stochastic multi-arm bandits problem is a special version of this matrix games, because if your matrix has just one column, that's essentially a multi-arm bandit problem essentially. So we are kind of generalizing from multi-arm bandits to matrix here. So yeah, so that's what we are doing.
So in other words, if I use multi-arm bandits algorithm for each row, and then
you mean for each player?
No, so basically, as you're saying, if there's only one row, then it's just multi-arm bandit, the matrix. If it is only one row.
Yeah.
So now if I use it for, okay, maybe it's not clear. Okay, fine, go ahead.
Like you like there are algorithms like EXP3, like adversarial bandits, where you can like run the algorithm for both the players and get good bounds. But we are like more interested right now to study the instance dependent guarantees of the matrix. Yeah, I'm not denying that such an approach might not work. It can work. I'm not denying that. But right now we are just trying to capture, okay, what can be the instance dependent guarantees that can arise here. Yeah. So I hope it's clear till now. But
I just had a question.
Yeah.
So I just wanted to know, when you're talking about sampling the matrix, it's sort of like saying that both the agents come together and say, okay, we'll sample this one. So it's not sort of adversarial, right?
No, we have control over our we have control over what we can sample.
So both agents sort of come together and say, okay, we'll sample.
So the thing is like I gave you the game theoretic aspect of this, but essentially what you have is like at the end, what you have is like you're given a matrix A, usually in game theory. I mean, forget the game setting, but in general, you're given a matrix A and you're asked to find a Nash equilibrium, which you can do directly using LP. Now, if you don't have the game directly, but instead you can sample, then you can kind of find some approximate solution. That's the aim of us. We are not like trying to essentially control two players and try to find solution. That would be a separate interesting problem, I would agree. But right now, I'm purely interested in just finding the Nash equilibrium, and I have this flexibility given to me that I can query any element of the matrix at any point of time. That's the basic thing actually. So you can think it in terms of like multi-arm bandits also. Like in multi-arm bandits, we have the flexibility of like choosing any particular arm and sample it. So you can multi-arm bandit is like it's a n cross 1 matrix. You can extend it to arbitrary n cross m matrix. So that's the rough idea.
So Arnab,
Yeah.
Quick question: which parameter of A will you use? Will you use all of when you say instance dependent?
Yeah, that's what I was going to actually. Yeah, I didn't come to it, right? That's the main part of the talk. Like, what are the right parameters to look at? Because that's not pretty clear actually. Yeah. So I hope the setting is clear. In case someone joined it late, I'll just like just keep it like this for 10-15 seconds in case people can have a look at this setting just to be clear what's going on. Yeah, so like you have a matrix and you have the total flexibility to choose any element and sample it and see what is the noisy value of that entry. And you can like repeat this process for like lot of times and you can get a pretty good estimate of the matrix A. The question is, do you need to do this in worst case?
The parameter may be sum of all the entries or something like that, because high entries may.
It's a bit more complicated than not just sum of entries. I'll say you why.
Yeah.
Let me go to that slide now. Okay. So before we go there, let me just present you an analogy. Like I'll be like drawing analogies between bandits and our game setting. So essentially, what you have is like you have like n arms with means mu1 up to mu(n) in multi-arm bandits, and your aim is to find this arm which has the mean mu1. So you can like pose it as a n cross 1 matrix, and the first row would be the optimal strategy, and there would be a gap of delta between the first entry and the second entry, like between the first entry and rest of the entries. So you can like in principle sample every element for 1 by delta square times and be done with the algorithm and find the best term. So that's the improvement that you get over 1 by 1 by epsilon square algorithm. So instead of 1 by epsilon square, you can do 1 by delta square. So that's the idea behind multi-arm bandits. Now the question
one
is,
question: delta can be much smaller compared to epsilon as well, or
yeah, like obviously it's minimum of 1 by epsilon square by 1 by delta square. So you have that trade-off as well. So you can sample and either you stop at minimum of 1 by epsilon square comma 1 by delta square time. That's the actual guarantee.
so you are looking at base term or epsilon base term. What is your goal here?
So here's multi-arm bandits. I'm looking at like multi-arm bandits. I'm just telling epsilon base term.
Okay.
Yeah. So an equivalent version of it in our games would be epsilon Nash equilibrium. That's the analogy I'm trying to present. Yeah. So now the question is, Okay, so we have like a concept of best arm in n×1 games. So say if we are looking at n×2 games, which was also the main focus of our paper. We do have like results for arbitrary n×m games, but we did not add it to our paper because those were not super tight or anything. But our main focus of the paper was n×2. I'll talk about n×m at the end, but let's focus on n×2 games. So in a game setting, you don't have anything called like best value or anything. Like there's nothing called best value like you had in multi-arm bandits. So what's the thing that you have? The thing that you have is obviously Nash equilibrium here that I was talking to you before. So assume that you have a matrix game which has a unique Nash equilibrium x star y star. Let me assume I'm trying to motivate the parameter. So let me also assume that this is not a pure strategy Nash equilibrium. By that I mean that essentially the support of these both distribution is not one. So so that's what I'm kind of assuming. So like using some standard game theory results, you can show that the support size of this distribution would be exactly 2. Okay. So essentially what you will have is like here you have the best row, which is like the best arm. In the matrix games, instead of best row, you'll have like support of the Nash equilibrium. So you'll have like 2 rows, which are part of the support of x star. So that's the analogy that you can draw from matrix and between matrix games and multi-arm bandits. So yeah.
So let me understand this.
Yeah.
So you're assuming that support is not 1 and it can be shown that it is 2, is it?
Yeah. If the support is 1, then the problem becomes very similar to multi-arm bandits only, because essentially you're trying to find the highest element in the column and the lowest element in the row. So there it's more or less like a bandit kind of problem only. So a more interesting problem would be to look at the case when support of x star is equal to 2.
I see. So effectively you're saying that A belongs to R n cross M, support will be less than equal to M.
Yeah.
Okay.
So in this case, is it like top 2 arms kind of things help, or it's different from that? Like it's not actually top 2 arms. If support is 2, size 2.
Yeah.
I mean, as you said, for support 1, it is like a base term kind of an algorithm. But
Yeah.
for support 2, if something from top 2 arms or something help, or maybe it's not actually top 2 arms, some slightly different. So it's not clear.
So that's not clear. Like what to do here, like because you have 2 things, and since the support is 2, it won't be the case that like these 2 rows will like dominate each other. Nothing like that would happen. Like let me take okay. So essentially, the thing that I want to say is that okay, this is kind of the submatrix which kind of captures the Nash equilibrium. Like this is the support and this is the support of the y place. So this red box, I'll be repeatedly calling it as like the optimal submatrix. So what essentially I want to do is like I want to find the notion of gap between this submatrix and the rest of the matrix actually. Like what is that particular gap which kind of separates this from this? Like in bandits, it's pretty clear, like it's a gap between the means, but in a matrix, it's not clear what's the gap between this submatrix and the rest of the matrices. Okay, so that's what we'll explore here. And once we look at that, more or less like figuring out the algorithm is not that trivial, but that our job will become easy. So to motivate like what this gap parameter might be, because this is the main focus of our paper. So let's look at 3 examples. Okay. So these are 3 different matrices, and I have like listed down their Nash equilibrium. Like these are x star and these are y star. So if you look at this particular matrix, these three matrices are pretty similar to each other. Like not exactly same, but they're similar. Only the elements in the last row is increasing by a small amount. And you can see that no row is like strictly better than the other row. Like by strictly better I mean like component wise they are not bigger than the other row. So 1 is greater than 0, but 0 is less than 1. 1 is greater than 0.05, but 0 is less than 0.85. And same is the case here. So in none of the matrices, none of the rows are better than each other. Then how do we like say, so for example, if you look at the Nash equilibrium here, so the Nash equilibrium here, the X star is 0.5, 0.5 and 0. So essentially the support is the first two rows. If you increase the value slightly, then you'll have like multiple Nash equilibrium. So it's no longer unique. So you can have like all these three rows part of your support. And if you increase the value even further, then the first and the last row becomes the Nash equilibrium, like the support of the Nash equilibrium. So what is happening here, which is causing this transitional change, like because here the support was the first two rows, then it became all the three rows, and then it became the first and third row. So there is some transition change that has happened. So we'll look at it now. So you take the Y star of each of these matrices and you do a dot product of this Y star with each of these rows. Okay. So you do the dot product with each of these rows. So what you get is, so what you get is like, if you do for the first row, you get 0.5, 0.5 and you get 0.45. And similarly, you get something like this. The key thing to observe is the red box is like the support. It captures the support of the Nash equilibrium. So if you observe that in the first matrix, these two rows were part of the support and the values corresponding to it is same. And then there is a gap here with the rest of the matrix. Now the reason here all the three came into the support was all the three values coincided. So there is no gap here. So the equivalent version in bandits is like two arms have same mean. So you can't like distinguish between them. So both are like best arm in some sense. And then you slightly increase the value again. And then again the dot product, you'll see that these two values are same and there is a drop actually from the third value onwards. So now you can see the gap that I'm trying to say, and this is exactly the gap that we are looking into the paper actually. So let's not go into the constants.
Can you
yeah.
Very quick question, sorry. Go back to the previous slide.
Yeah.
One more. Yeah, just okay.
Yeah.
So you said there can only be two X star Y star. But in the third case, equivalently, you can substitute 0, 4/9, 5/9, right? Like that is also.
Where is it here? Here you mean?
Yeah. Yeah.
0, 4/9, 5/9. It definitely won't be a Nash equilibrium. You can try and check it.
Okay.
Yeah, there will be some deviation either from the there will be a deviation from the X player itself directly, because the reason is like you fix Y star, so so essentially the X player can, whatever X player plays will be a convex combination of this, and it would be better for the X player to play the first and the third column because that gives you maximum reward.
Okay.
Playing the second. Yeah, playing the second column, second row will actually give you less, so you can always do better.
Okay, thank you.
Yeah, so so this is roughly the notion of gap that you're looking at, like these gaps actually, the gaps that you see here. So to be precise, like you ignore all this stuff, let's focus on this part. So VA star was the value of the game, and y star and this thing like is essentially taking the dot product of y star with the rows of the matrix, and this I1 I2 is like the support of the Nash equilibrium. So obviously the support of the Nash equilibrium, those values will be the gap between that and the value of the game would be 0 naturally. So you have to look at the gaps from the third entry onwards, like this particular gap. So these are this is the exact gap parameter that we would be focusing on roughly. Yeah, so any questions till now? Like I hope the notion of gap is clear, like how the gap came upon and what we should be focusing on is I think it should be clear. So the thing is, why are we looking at this gap? It's like, okay, let me just, yeah. So the thing is like, I don't think I'll get time to go into 2x2 case, but like think it in this way, like I have this entire big matrix. In worst case, I can just sample every entry for 1 by epsilon square times and be done with it. But what I'm saying is that instead of doing that, maybe first you can sample each entry for 1 by delta g square times, and you can quickly identify this smaller matrix. Okay, so that's the key idea. And then once you identify the smaller matrix, then maybe you can do, for example, 1 by epsilon square on each of the smaller entries. Like you can do better than that, like just like blindly doing 1 by epsilon square. You can do slightly better than that. But I don't think I'll get time to cover that. But to give a high level idea, instead of like just naively sampling each entry of the matrix for 1 by epsilon square times, what you can do first is sample each entry for 1 by delta g square times. Delta g might be a very big quantity compared to epsilon. Then you can you can estimate this smaller matrix, and then once you estimate this smaller matrix, then you can like it's just a 2x2 matrix. Then you can like run some algorithm pretty quickly and find Nash equilibrium there. So that's the key idea. So I hope.
So one question, like,
yeah.
As you are doing this n cross 2, so you're restricting for one pair there is only 2 strategy, another pair there is n strategy.
Yeah, this is just to give you an intuition what's going on. Like, okay, in our paper we did restrict ourselves to n cross 2 because at that time we didn't have any results for arbitrary n cross m. But later on, we got a similar analogy for n cross m matrices. So like these results extend to arbitrary n cross m matrices.
But in general, if you have like n cross m matrices, then if I take all these m choose 2 permutations, basically all.
No, you have to be a bit clever there. You can't just do blindly m cross 2. Like what will happen is that the key thing that you have to notice is that if you do the dot product of, the key is not to take this m choose 2 combinations. I'll come to that actually, how we can actually cleverly find. But essentially the key part is that the dot product of these y stars is creating the gap. And same, if there's a larger matrix lying around there, if you do x star, that will also create a gap. So the idea is not to do like take m choose 2 combinations and then try to figure out the gap. That's a pretty naive way to do that thing actually. There's a way clever way to do actually. That's what I'll discuss and maybe wrap the talk with that actually. So let me just.
Hey, sorry, quick question.
Yeah.
So we are working with noisy versions of
noisy version.
And therefore, like you might want to add gap plus eta or something, eta noise.
Like okay, so
but that may be for cumulative because you're now fixing a particular.
So I'm looking at the original matrix and I'm trying to determine what I'm just looking at what the gap might be.
Oh, right. Okay.
Yeah. And then the rough idea is like this the like if you want to take away from this talk, the takeaway is like if you manage to sample the matrix for 1 by delta G square times, like delta G being the gap, and stop, then you can easily identify the optimal submatrix and maybe return it. That's the rough idea. Now, there's lot of stuff that is going on here, so that's what I would like to cover. But this is roughly what I would like to show. Like what I would like to show is that that I can like sample every entry for 1 by delta G square times, and then stop the algorithm and just look at the empirical matrix and just look at its support, Nash equilibrium support, and that would be same as the original matrix support. That's my aim actually right now. So let's see let's see at the algorithm to find the support. Okay, so just to give you, let's go step by step and see how we can like do the things. So this is the gap that we are looking at, which is roughly the gap between the VA star and the, as I was saying, the dot product of Y star and the rows, except the support. So that's the gap that we are looking at, like essentially this particular gap. Now, so what you can do is like, say you can look at the empirical matrix. So say you have sampled for some number of times and you can look at the empirical matrix. And say, for example, say this X star, Y star is an Nash equilibrium of A bar, and you can look at the empirical gap also here. So the thing is that suppose, okay, this is not an assumption in the paper. I'm just, for the sake of the talk, suppose that you know the value of delta G. Okay, you know the value of delta G. Then what you can do is that you can sample every element of the matrix for 1 by delta G square times. And then what will happen is that, so this is the optimal submatrix, and this is the corresponding submatrix in the empirical matrix. So when you sample for 1 by delta G square times, you will observe some empirical gap, which is like delta bar G. And like, I'm not showing the calculations, but what you can show is that these both gaps would be pretty much close actually. Okay, if you sample the matrix for 1 by delta G square times. So essentially, if you sample these many times, you'll see some gap being created in the empirical matrix. And that will give you an indication of what the gap is in the, where the, what is the support of the Nash equilibrium in the original matrix. So that's the idea, like sample sufficiently so that this support kind of separates from rest of the matrix as time proceeds. And so you can clearly see that, okay, in the empirical matrix, this is a support. So that must be the support in the original matrix. So that's the key idea behind the algorithm. But there are a lot of challenges here actually. So we'll address the challenges one by one. But before I go there, like, is the rough idea clear what I'm trying to do?
Yeah, I have a quick question. So earlier we thought we could sample some of the entries less and some entries more.
Yeah.
For example, the gap might be created early and then you can ignore certain rows and so on. Is that possible? Just like median elimination for
I'm not denying that. It's possible. You can do even something which is much more clever than what I'm doing, and maybe improve the algorithm in some sense.
Okay. But you're showing that it's sufficient to sample everything delta G, 1 by delta G.
Yeah. And what I also did not show was, like, we showed also a lower bound that you are required to sample. Okay, we showed it for 3x2 matrix. So if you have a 3x2 matrix, you are required to sample for 1 by delta G square times. So at least as long as this, if you ignore a factor of n, in terms of delta G square, it's optimal actually, the strategy. So But you can still like improve it and slightly improve the bounds. Like, okay, there might be, you can, there's still a scope of improving the bounds. I'm not denying that. Yeah. That would be also a cool thing to look at. Yeah. But in general, I guess the rough strategy is clear, like what I'm planning to do now here. Yeah. Arindam sir, is it fine so far?
Yes, fine.
Okay, cool. Yeah. Now, just let me point out to you here, like this x bar star, y bar star is like the Nash equilibrium. I shouldn't have written like Nash equilibrium of A bar. What I meant was like if this is the optimal submatrix, and if you look at the optimal submatrix here, then this optimal submatrices Nash equilibrium is like x bar star, y bar star. That's what I meant in some sense. Now the thing is like, okay, if you can like observe this value here, this particular value in the matrix, then what you can do is like what is easy to show is like you can sample the every entry of the matrix for say 1 by delta square times, and like show that delta G minus this empirical version is at most delta. Okay, so in 1 by delta G square times, we can have a very good estimate of delta G and we can be done. Okay, but can anyone just say what is the problem with this particular thing here? Like, what is the problem with this particular version of an empirical thing of this thing, delta G? So, okay, so the main problem is if you look at this empirical version, it relies on the fact that I doesn't belong in support of X star. And that's the thing we are trying to find actually. So we don't know support of X star. So we can't measure this delta G bar directly. So that's the main challenge actually. So if suppose like if like for instance, I tell you what the support is, like for a second, forget that I'm trying to find the support, but instead assume that I'm just trying to estimate delta G, and I tell you what the support is, then it's very easy to estimate what delta G is. Like just look at this gap and be done with it. But that's not possible because we don't know the support of X star actually. Instead, what we can measure is this particular thing. So if X bar Y bar is the Nash equilibrium of the empirical matrix, then you look at the gap in the empirical matrix. Okay, so here you have like support of X bar, not X star. Okay, so you start sampling and you start observing the gap in the empirical matrix. Do note that the matrix that you're seeing here, this need not be same as the original matrix actually. Yeah. So this, because that's not guaranteed. So for example, so suppose if this is the original matrix, original support of the matrix, then the matrix optimal support of the matrix that you're seeing in the empirical thing can be lying somewhere here down. It need not be this thing exactly. So that's what I'm trying to say. So if you look at the support of X bar, that may not be equal to support of X star. Okay, so that's the major hurdle that you have here. So, but the thing is that you can only observe like delta G bar. That's the only thing that you can observe. You cannot do anything better than this. So how do we kind of save ourselves? So the kind of like the saving grace that we have is like, so say this is the support that you see in the empirical matrix. Okay, and say this is not the support of the Nash equilibrium that we are trying to find. So if you look at the original matrix and look at this particular part of the matrix, and you try to do a similar gap notion with respect to this matrix, then what you'll see is that the gap will be negative for one of the rows actually. So essentially, if you try to compute this quantity, VA star minus minimum of this I, this is not belongs, this not belongs. If I does not belong to support of X, and this dot product where X comma Y is the Nash equilibrium of this submatrix. If you look at this submatrix and try to do the dot product with respect to the Nash equilibrium of this submatrix, for some row you'll see that the gap is negative actually. So that's pretty crucial actually for us. And this we can show that the gap will be negative if you're not considering the optimal submatrix, and if you're considering the optimal submatrix, then only the gap will be positive. So what that means is that in the empirical matrix, this estimate delta G would be at most delta if we sample for 1 by delta square times. So that's the rough idea. So what we'll do is like we'll sample each element. Say we have sample for 1 by delta square times, and this is the estimate that we have of the gap, and we'll stop only when this delta this estimate becomes greater than delta. Okay, like this delta would be like decreasing because that's the number of times we are sampling. So we'll only stop when delta G, this tilde is greater than delta, and then we return the support of the Nash empirical matrix. So a key thing to observe is we will never return the wrong support. Okay, because this condition will hold only for the optimal submatrix. For the suboptimal matrices, like for other matrices, this is the condition that holds, and you cannot. So this condition will only hold when the matrix, the empirical matrices support matches with the support of the original matrix. So that's the rough idea. Now, there's still one issue actually here. Still, it's not completely resolved. The reason I say that is, what if this condition never holds? Okay, like what if this never holds for any time steps? That's one possibility actually. So we'll never stop essentially. In worst case, we'll hit again 1 by epsilon square time in some sense. So what you can show is that that this estimate, okay, this estimate that we have, and if you compare this estimate to this delta G bar that I was discussing before, like which is the gap with respect to the optimal submatrix. So let me just go back quickly. So this was the delta G bar. This is the gap with respect to optimal submatrix, but we may not have the optimal submatrix right at the start when we are sampling in the empirical matrix. So only thing that we have is delta G, this tilde. So the thing is that you can always show that this delta G tilde is greater than or equal to delta G bar. You can show it pretty easily. And since delta G is like a quantity, since delta G is a quantity which is greater than 0, its empirical estimate, which is like delta G bar, after some point will eventually become greater than delta. So in that case, this this delta G tilde will also become greater than delta and will be done. So roughly what I want to say is that there will be a time step when this particular condition will hold. Okay. And once this particular condition holds, we can stop our algorithm there and just return the support of the empirical matrix. So in this way, we can find the support of the empirical matrix. And once you have the support, like in this case, a 2x2 matrix, we can run some clever algorithms and slightly improve our bound. Like in worst case, it will be still 1 by epsilon square, but you can do slightly better than that. Like let me just give you one example. But before I go to the example, does anyone have any query? Because this might be a bit confusing. So feel free to ask any questions that you might have here for this idea behind the algorithm to find the support of the Nash equilibrium.
Hello, Arnab.
Yeah.
When you say that delta G bar will be attained at eventually, so that means timestamp greater than 1 by delta square and between 1 by epsilon square. So that is the timestamp when it will eventually hit this.
Oh, like roughly, like when this delta becomes like delta G roughly, that's the moment when you hit this condition actually.
Okay.
Yeah. So essentially, like delta is like decreasing, like delta, you can think that of a confidence gap on the elements that you have sampled. So delta is a confidence on the element. So like you need to sample 1 by delta square times. So as you decrease delta, like it means that you're increasing the number of times you're sampling, and at some point it will become less than delta G. And roughly around that time, this condition will hold. So that's the key idea.
Okay, yes, sure.
Yeah. But the rough thing is that unlike bandits, where you can like kind of see the gaps directly, here to summarize, here you have like two challenges. Actually, you have the one main challenge, which is like this is the original gap parameter, and we don't have any way to estimate it directly. Okay. Like you can always look at an empirical version of it in the matrix, but the main issue with that is we don't know the support of the Nash equilibrium. So this delta G prime, delta G bar is just an empirical version, direct empirical estimate of delta G. Nothing special going on here. In bandits, we have we have direct empirical estimates on the gap, so we are fine actually. But here we don't have this luxury because we don't know what the support is. So instead, what you can do is like you can just look at the gap of the empirical matrix, and that gap need not that gap need not be an estimate of delta G. That's the main message. But eventually, as you sample sufficiently, it will actually become an estimate of the this delta G. The main reason being that because for this, like if it is okay, the thing that I want to say is that the submatrix that you're looking at right at the start, it need not represent the support of the Nash equilibrium of the original matrix. But as time proceeds, eventually it will become the support of the Nash equilibrium. And the reason is this particular inequality that I showed. The estimate would be less than delta whenever this matrix is not the optimal submatrix, or it's not the support of the Nash equilibrium, but delta is decreasing with time. Okay. So eventually our estimate will become greater than delta. And in this case, we'll have our optimal submatrix. And
so two questions I have. First is that delta tilde may not be monotone, so it may go up, go down, and so on. So at some point it can hit and then not get hit in subsequent ones. That is a possibility.
So the thing is that once so you can establish some confidence gaps around this delta G, like how badly it can behave actually.
Yeah. So that might take care of it. The second question I had is what so if you go few steps back, you said you don't know which is a support. Because you don't care about time complexity, can you not consider all possible supports?
Yeah, but then the question is which one would you consider, even if you find, because there might be like multiple candidates, right? So I'm not denying that's not a possibility, like that's not a strategy, but think of it in this way. Maybe for 2 cross 2 you can, like for n cross 2 you can take all possible submatrices of size 2 cross 2, but what about higher dimensions? Like it's totally infeasible to do that, because then it would, like, I know you can avoid looking at time complexity, but still it becomes a bit cumbersome and you have like multiple candidates, and that's why we did not go via that approach actually, like, because then it's a tough thing, right? Which is the actual candidate to look at? It's not so clear actually. So that's why
Okay.
that's why you wait for the matrix to automatically reveal the actual support. Like if you know that you can sample if you sample sufficiently, then you will eventually see the support. The main concern is you don't stop too early. That's the main concern, and this is the exact inequality that avoids us from stopping early. So if we like keep this as our stopping condition, then none of the bad options would get in our way. Only the desired output will be only returned. So that's the key idea actually behind the algorithm.
So let me understand this. Sorry, one last question. Let me understand this further. Say, let's say you're sampling, there's an approximate matrix. Because of noise, for some reason, delta tildes are all zero.
All zero? Yeah, it might be possible. Yeah.
So then you stop, right?
No. I want my delta tilde to be greater than this delta.
Oh, okay. Greater than.
Right. Yeah, greater than. Yeah. And it's only possible for the optimal submatrix.
Okay.
Yeah. It's not possible for any other submatrix. Yeah. So
Arnab, can you wrap up in, let's say, 3-4 minutes?
Yeah. I'm done actually. Like.
Okay.
But Arnab sir, are you clear with this? Like why I did not go for M choose 2 here?
Yes, this part is clear. Yes.
Yeah, that's why. And if you can actually extend this algorithm to n cross m by going by similar principles. Yeah.
Okay.
Yeah. So I'll wrap it up. So like 2 cross 2 is pretty simple. I'm just skipping it. But the thing is, like, you can extend our techniques for the case of n cross m to find unique Nash equilibrium in the game. But we doubt that our instance dependent guarantees are totally optimal. And as someone was suggesting, they can try different methods to actually improve. So definitely it's not super tight, and it's not at all tight in n cross m games. So the main open question that I leave you is like you to find tight upper and lower bounds for n cross m games in this setting. Yeah, so that would be it. So thank you. Yeah. And I'll share these slides also, maybe with Debojyoti, and then Debojyoti can circulate it because there are some content that I skipped actually. Yeah.
Yeah, sure.
Yeah, but this is what I had to say roughly. Yeah.
So couple of questions.
Thank you, Arnab. Yeah.
Yeah. Where is the
please
meeting going on? I didn't. Where is the meeting going on?
I can't see the meeting. Okay, fine.
So a couple of questions. One is like, okay, zero sum property you're using because it's only one metric. But if you don't have zero sum properties, there are some other notions which can be. I mean, there are two matrices, different payoff matrices.
Yeah.
Is there some way of defining similar stuff there, or?
It's very. I don't see a way because I heavily use the fact that this gap parameter will be there actually. Like there will be some gap.
Okay, if we are not looking at instance dependent case, but let's say other case that you mentioned that there are some EXPC type algorithms which are used for So those settings, is it possible to define something similar? Are there other algorithms for non-zero sum games?
So in non-zero sum games, what people mainly focus on is like not computing the Nash equilibrium because it's hard. It's more about computing other equilibrium, like there's like correlated equilibrium,
Course correlated or correlated.
Yeah. So for those kind of problems, it's like kind of open. We did not explore anything there. Like the worst case sample complexity bound is usually not sample complexity bounds. Like in game theory, they call it external regret, but in some sense they look it in terms of that external regret and try to minimize regret, and using that they can give some sample complexity bounds, but they are like minimax in nature, like worst case bound, but you can achieve it using bandit algorithms, I mean.
Okay. And also in the last case, you assume this pure Nash, assumption of pure Nash. Why was that required? Like if you don't have that,
where did I assume?
The maybe last slide somewhere you mentioned it for n cross n games with pure Nash equilibrium.
No. I mean, you mean this actually?
Yeah, this one unique, not pure, sorry, unique Nash equilibrium. Okay, yeah, unique. So if it is non-unique, then what is the problem?
Oh, the thing that we showed is that if the game has non-unique thing, then you will require.
Okay, right. Oh, yeah, you mentioned right.
Yeah.
Okay.
Yeah, if you'll require 1 by epsilon square samples irrespective of the instance of the matrix, because what happens is that the gap, to be precise here, okay, so the gap falls down to 0. So if you add noise, it would be pretty difficult for us to differentiate between this matrix and these two matrices actually.
Yes,
so you can't tell where you are lying, whether you are lying here or here. And depending on where you lie, your Nash equilibrium can change drastically. So that's why if you don't have uniqueness, then it's very difficult to find the Nash equilibrium. I mean in terms of sample complexity.
So a general question, like basically you are trying to find some property of the matrix. Nash equilibrium is one property, but some other property. So are there any other properties known, like not Nash, but which can be useful in practice or which are useful in practice for this kind of sampling algorithms?
You meant in terms of like instance dependent or in general?
In general, let's say.
In general, there are these matrix norms and there are matrix inequalities.
Right. So those things, without the instance independent case, something is known there, or like sampling stuff. Maybe it's already studied a lot.
Yeah, I'm not that sure, but the only thing that I know in general is like you have like matrix inequalities for which is like where they deal with norms, eigenvalues and all. So if you sample sufficiently, your eigenvalue is pretty close, but they do it under some assumptions like symmetric, PSD, those kind of things. Yeah. So that's the case actually.
I think I've seen some papers with David Woodruff where they were doing something like that.
Yeah. I'm wondering where the meeting.
I had a question here. So I was wondering whether in this setting so this is very similar to simple regret setting where like you sufficiently sample and then check for whether it's less than 1 by epsilon square. I mean the gap is lower than epsilon, but is there anything cumulative?
Good question. Let me paste a paper which kind of talks about cumulative, and actually we are even like, is the recording going on or is it stopped?
Yeah. It's going on? Yeah.
Oh, can we stop it? I guess we are just chatting right now.
Okay. Fine. Yeah. Let's stop the recording.
Yeah. Let me just share a paper.